So the second lecture from the carbanions, we start with the reactions involving carbanions. So carbanions in alpha halogenation reaction of ketone. Ketone in alpha halogenation, this reaction, the alpha halogenation of ketone is a classical organic reaction where one or more hydrogen atom on the carbon adjacent to the carbonyl group, the alpha carbon are replaced by halogen. Typically طبعا Cl2, Br2 or iodine. This reaction is unequal because it can be catalyzed by طبعا either an acid or base. Both of them can be used to catalyze this type of reaction, but the products and stopping point here, we said to stop the reactions of these two pathway are different. So I will give you example here. Just for example, this is the alpha halogen at alpha carbon adjacent to the carbonyl group. Okay, this acidic. So can be removed. This proton can be removed by base if our reaction is catalyzed by base. So replaced by the halogen. So it will give you alpha haloketone. It will give you alpha haloketone. So the same thing here. This is the acetone Br2 NaOH, so it will be replaced alpha proton, it will be replaced by halogen. The same thing here, cyclohexanone, it will be replaced by halogen. The same thing here, alpha proton here, it will be kind of replaced by the halogen. This the reaction. So here we have important thing in this type of the reactions is the ketoenol tautomerism. Ketoenol tautomerism is a chemical equilibrium between keto form of a ketone or aldehyde and the enol form. So this is the keto form, this is the enol form. So an alcohol with a double bond. This alcohol with double bond, we said enol form. While they might look like resonance structure, it is like resonance structure, they are actually constitutional isomers. It is not resonance structure. It is constitutional isomers because we have different arrangement of the atom here. Here CH3, here CH2, or oxygen, or OH. That meaning is different rearranged. So that is not resonance structure. Okay, it is not. Again, it is not resonance structure. It is constitutional isomers. So how this it will be converted to this? How this it will be converted to this? طبعا by a mechanism and also can be catalyzed by acid. Here catalyzed in ketoenol form by catalyst. Acid catalyst here will be used protonate and oxygen first, making the alpha hydrogen more acidic. So here acidification, it will be protonated the OH, oxygen, it will be protonated, and now remove the alpha proton to give this enol tautomerism. By base catalyst, also, the base firstly remove the proton and make the double bond and the pi bond here between carbon and oxygen open to the oxygen to make oxygen minus. And the next step, the negative charge on the oxygen, it will be protonated. Then the oxygen will be protonated from the solvent that be used. For example, here the water, take a proton from the water to give the enol tautomer. So enol tautomer, that meaning alkene, enol, alkene and alcohol group, enol tautomer. Acid catalyzed alpha halogenation of ketone. In acidic condition, we come back again to our reaction, the alpha halogenation of ketone. So in acidic condition, like acetic acid or HCl, it can be used also during this reaction. The reaction usually stop after one halogenation has been added. So why the reaction will be stopped after one halogen? It will be added here. Will be C. The intermediate, the reaction proceed via an enol intermediate. The intermediate here it will be enol. Regoselectivity, if the ketone is asymmetrical, halogenation occur at the more substituted alpha carbon. If the halogenation again, if if the ketone unsymmetrical, okay, the halogenation it will be occur at more substituted alpha carbon, the one that form more stable double bond in the enol. So as we know here in the enol alkene, of course, when increase the R group, the stability of the enol it will be increased, and the forming for the double bond. Why it is stopped? Because one halogen is added, it is electron withdrawing nature, making the oxygen less likely to pick up a proton, making it harder to form second enol here. So look, when the first halogenation will be occur, look, it will be take a proton, then this base remove alpha proton to give you the enol form. So the enol form again a shape of electron make double bond, and the double bond take halogen, take the halogen from here from the Br2 to give you this intermediate. So deprotonation remove proton from the oxygen to give you this final product has alpha halogen on the alpha carbon. So when this alpha halogen is substituted, it will be withdrawing. This halogen it will be withdrawing, and make this shape of electron, or the electron density on the oxygen it will be decrease the electron density on the oxygen. When the electron density on the oxygen decrease, that meaning this step again cannot be happened, and the reaction will be stopped at just one halogenation on the carbon. So this molecule cannot be entered to the acidification again. يعني this shape of electron cannot be take this proton again, cannot be take this proton again, and to repeat all the step again, and it will be stopped. It will be stopped to here. This about acid catalyzed. Acid catalyzed. For this reason, it will be stopped reaction. Just one alpha halogenation will be happened, and it will be reaction will be stopped. When we used base as catalyst, in basic condition like NaOH, the reaction is much more aggressive and often lead to the multiple halogenation. That meaning here we have a problem. Here multi-bromination or chlorination, multi-halogenation will be happen. So the intermediate here, the reaction proceed via carbanion enolate intermediate. Why it is continue? يعني not just one halogenation will be happen. So the halogen are electron withdrawing. One on the halogen is attached to the alpha carbon to make the remaining proton on the same carbon more acidic. So that will be base. It will be easy to remove the second and third proton. So the base will be kept stripping proton and adding halogen until no alpha halogen it will be remain. So look here, the base remove proton, make carbanion, and this carbanion is resonance to give you this structure. Finally, this make double bond and pi bond take a proton to give you. Now this halogen here withdrawing. So it will be decrease if you have hydrogen here, for example, hydrogen here, and this base hydrogen, it will be decrease the acidity of this hydrogen. It will be decrease the acidity of this hydrogen and remove it, and the second bromination will be happened, and third bromination will be happened, until all the halogen will be replaced by the alpha halogen atoms. It will be replaced by the halogen. So example for this reaction, also it is important reaction in identification for the methylene ketone compound is the haloform reaction, oxidation of methyl ketone or iodoform test. This important test for ketones to distinguish the ketone from the other compound. So the iodoform test is a famous lab test where appearance of yellow precipitate. This when it will be as side product CHI3, it will be as yellow precipitate. Confirm the presence of methyl ketone. So If there is any yellow precipitate, that meaning we have methyl ketone. So a special case of base promoted halogenation occur with the methyl ketone ending to the side. If you treated the methyl ketone with excess halogen and base, the alpha carbon is halogenated 3 times. So the alpha, it will be halogenated 3 times. This creates CH3 group, which is the decayed leaving group. It will be as leaving group. The hydroxide then attack the carbonyl, kicking out the CX3 as shown here. Now, iodification. Second iodification will be happen. Third iodification will be happen. It will be all this hydrogen atom. It will be replaced by iodine. So finally, when this base added to the carbonyl, it will be as leaving group. It will be leave the structure as what? As CHI3 yellow precipitate. Okay, and the second part, it will be carboxylate anion and basic medium. So it will be give positive results for methyl ketone compound. Carbanions as nucleophile in nucleophilic addition to aldehyde or ketone. So the first important reaction here, we have aldol reaction. Reactions of aldehyde or ketone to give beta hydroxycarbonyl compound. Beta hydroxycarbonyl compound. If this beta hydroxycarbonyl compound go further to lose H2O molecules, it will be give you double bond here. It will be called aldol condensation. So reaction of aldehyde or ketone to give beta hydroxycarbonyl compound. This is the beta hydroxy. Addition, the reaction will be happened like that. Here the mechanism. Firstly, the addition of the alpha carbon of an enolizable aldehyde or ketone number 1 to the carbonyl group of the second aldehyde or ketone. This here. Okay, this it will be added to here. So it's called aldol reaction. It is important method for formation of carbon-carbon new bond. Okay, for carbon-carbon new bond, and is frequently used in organic chemistry. This is very important in organic chemistry. The initial reaction products is beta hydroxyaldehyde, aldol, beta hydroxyaldehyde, aldol, that meaning aldehyde and alcohol, aldol, or beta hydroxyketone, ketol. So the subsequent, the dehydration step, as I told you, if go further to lose the electron, it will be give you alpha beta unsaturated carbonyl compound. And in this condition, it will be aldol condensation. So the reaction can be preferred with the base catalyzed as well as acid catalyzed. Both of them can be used as catalyzed for this type of reaction. The former is more common. Here, the enolizable carbonyl compound 1 is deprotonated at alpha carbon by base. So by base, we remove this proton, this or this, to give you carb anion, to give you enolate anion, and this enolate anion stable by resonance. So the next step, the carb anion will be added across to this carbonyl group, and this it will be open to give you beta hydroxycarbonyl compound, beta hydroxyaldehyde or ketone. Finally, if you this loss H2O molecule by additional work, it will be give you alpha beta unsaturated compound. If the initial formed beta hydroxycarbonyl compound still has alpha hydrogen, look, we have alpha hydrogen has, as subsequent elimination of water can be take place, leading to alpha beta unsaturated aldehyde or ketone. In some cases, the dehydration occur already under the aldol reaction condition. In general, it can be carried out by heating in the presence of acids. So sometimes directly it will be give you alpha beta unsaturated carbon according to the condition that we use in this reaction. So this about the mechanism. This about the mechanism. So again, this is the mechanism, step-by-step mechanism, base catalyzed enolate formation, the formation of the enol, the base remove alpha proton to give you the enol, the carbanion. This carbanion is stable by resonance. So then the carbanion will be attack. We said nucleophilic attack. This nucleophilic carbanion will be attack. They will attack the carbonyl carbon of the second molecules. So third step is the protonation. The oxygen minus take a proton from the solvent to give you aldol. Also, final step is the dehydration. The base remove the alpha proton, again alpha proton, and this give you carbanion. It will be make double bond here, and this it will be leave the structure to give you alpha beta unsaturated aldehyde or ketone. This about the mechanism. Look to this example again here. Hydroxide anion take alpha proton, give you carbanion. This carbanion will be stabilized by resonance, and then the carbanion will be added across to the carbonyl group to give you this intermediate product, and the oxygen minus take proton from the solvent to give you the OH. Finally, OH with the hydrogen, it will be remove minus H2O to give you this molecule. So I think we have mistake here. Some part here it will be not founded. So you have to add it here. Add this part, like this part, added here in this position. And this position, I don't know, it is not clear for me here. And also add hydrogen. Same thing here, added hydrogen. And this it will be lost water to give you this. So it will be exactly like that. Now this it will be loss H2O molecules to give you this final product. Overall reaction, it's two molecules, you have to add two molecules from the cyclohexanone to give you this product. Also, what we have here, another example. Look, acetaldehyde by diluted NaOH give you 3-hydroxybutanol. How it will be like this? To give you carbanion it will be add, and this take hot water. So this is Aldol reaction, not condensation. Aldol reaction, because until now it is not lost H2O molecule. So with unsymmetrical ketone having a hydrogen at both alpha carbon, a mixture of product can be formed. This is a problem for Aldol reaction. In general, such ketone react at the less substituted side to give the less sterically hindered product. Okay, this it will be the measure of product. For this example, if we for example 2-butanone, this is the 2-butanone. 2-butanone it will be entered to the aldol condensation, and the measure product it will be 5-methyl 4-heptanone. Here, this is the measure product. So the minor product, if you want to write the minor product as homework for you, make the carbanion here, and the carbanion will be attack this carbonyl to give you the different product. Okay, to give you the different product. But the measure product, this is the measure product. So across aldol condensation, what meaning across aldol condensation? Is variation of the aldol reaction where two different carbonyl compound, aldehyde or ketone, react together to form single product. So different aldehyde or ketone, it will be react together to give you the single product here. So this is a cross aldol condensation. If you look this the formaldehyde, and this is the propanal, also aldehyde. So the carbanion will be formed from this molecule, not from this, because here we don't have alpha hydrogen. We don't have alpha hydrogen. So the carbanion will be formed from here and it will be add finally to give you this compound. To give you this compound. If the product of aldol condensation under basic condition is benzyl, okay, like this, okay, is the product is benzyl, this is the product benzyl, it will be directly loss H2O molecule to give you alpha beta unsaturated carbonyl compound. You don't need work up for this type of compound. Directly to be give you alpha beta unsaturated compound. Don't give you this compound, beta hydroxy aldehyde or ketone. Okay, so a different situation is found in case cross aldol condensation, it's also called a Claisen-Schmidt reactions. Here the problem arises that generally a mixture product can be happened. Okay, can be happened if you have here a different aldehyde or ketone. Both of them has alpha proton, like this has alpha proton. So a mixture product can be found. A mixture product can be found. طبعا carbanion can be formed from here to give you this carbanion. Carbanion may be add to itself or it will be add to B. If the carbanion add to itself, it will be give you this compound. If the carbanion add to B, it will give you this product. The same thing here. Carbanion from here, this is the carbanion. If the carbanion react with the B again, it will be give you this compound. If the carbanion react with A, it will be give you this product. So a cross aldol can also be done between aldehyde and ketone to yield one product. The enolate carbanions from the ketone add to the more reactive aldehyde. Ketone usually add to the carbonyl group of an aldehyde. So the note here, the ketone usually add to the carbonyl group of aldehyde. The ketone, it will be add to the aldehyde. طبعا because the carbonyl of the aldehyde is more reactive than the ketone, so it will be accept the nucleophile, it will be add across to the carbonyl, and to give you the product. So the intramolecular aldol addition here, the intra meaning it will be the same, it will be happen the addition or the condensation or the coupling, it will be happened at the same molecule. So an intramolecular aldol condition is the chemical reaction where a single molecule containing two carbonyl group like dione or dialdehyde react with itself to form cyclic ring, shape a product. It will be give you cyclic product. Example here, anti-molecular aldol reactions 2,5-hexadione, especially explain why طبعا certain rings form while other don't based on the ring stability طبعا. Of course here, so if you look to this compound 2,5-hexadione, this 2,5-hexadione, so the carbanion will be formed from here or from here. This it will be attack this carbonyl to close it to give you 5-member ring. So if you make the carbanion like this case below, the carbanion here, this cannot be formed this 3 cyclic because the strength of the cycle. This cycle not stable. So need much energy to close the carbanion, the new carbon, to this carbon atom. So all the times the 5 or 6 member ring is preferred for other sides of the rings, from other sides of the ring. So the reaction to the up 5 member ring are highly stable and have very little ring strain. There is no much strain in this cycle. Therefore, the reaction proceeds smoothly to form hydroxy ketone or product this cyclic compound. The unsucceeded reactions, the reaction in the bottom here, uh, 3 member rings having extreme ring strain. Extreme ring strain, that meaning the ring strain here is so much, bond angle are forced to be 60 degree instead of the ideal 109.5 and half degree. So it will be not stable. It will be not stable. It will be not stable. So example again here, another example. Look here, from here the carbanion, it will be close to here. طبعا it is so far يعني to attack this carbanion and this carbanion, and the conformation of the molecules is preferred to make this carbanion to attack this carbanion to give you 5 member ring. Is about the molecular shape. Okay, is about the molecular shape. So the reaction to the up here, as indicated by طبعا by false and not formed, the 7 member ring are difficult to form. This is to do the entropy of two ends of such long chain have harder time finding each other in space compared to shorter chain. So it is so far to this nucleophile to find this alkytrophile and to make carbon-carbon in your bond. To make carbon-carbon in your bond. The reaction below here, the reaction, the 5 member ring here, the 5 member ring طبعا it will be good for the formation. It will be easy to form it. It will be easy to form it and easy to attack the carbanion, easy to attack this carbanion. Okay, so as a note for you, when diketone can form two different rings, it will be almost always form 5 or 6 member ring because they are most stable. They are most stable. They are most easily to form it. This important note for you. This important note for you. So the second type of reaction is related with aldol reactions is Perkin reaction. Perkin reaction. Perkin reaction, condensation of aromatic aldehyde with carboxylic anhydride. So we have carboxylic anhydride. It will be condensed with aromatic aldehyde. It will be condensed with aromatic aldehyde to give alpha beta unsaturated carboxylic acid. So the aldol-like reaction of aromatic aldehyde 1, this with carboxylic acid anhydride, this is referred to the Perkin reaction. This reaction of aromatic aldehyde with anhydride is called Perkin reaction, is referred as Perkin reaction. And alpha beta unsaturated carboxylic acid will be obtained. The beta aryl derivative 3, this is also known as cinnamic acid. This is compound for cinnamic acid. So the R group derivative of cinnamic acid. Tamam? This is the cinnamic acid. Phenyl and double bond carbon and carboxylic acid. This is the cinnamic acid. So benzaldehyde here, it will be react with this carbanion here to give this intermediate, and finally this enter to the alpha beta unsaturated to give you double bond. Finally hydrolysis, that meaning this H2O it will be react with this carbonyl, and this it will be as leaving group to leave as acetic acid and give you finally the alpha beta unsaturated carboxylic acid compound. So look, benzaldehyde with anhydride, directly this part here, this part, it will be add to this here. It will be add to here. That meaning we have carbon, carbon, new bond. This is the carbon and this carbon and new bond. Look to this example. What we have? Firstly, we have a Perkin reaction between this aldehyde and this anhydride. Okay, to give you the product, but not this final product. To give you طبعا alpha beta unsaturated carboxylic acid, and then alpha beta unsaturated carboxylic acid enter to the cyclization with this oxygen minus. This oxygen minus, it will be take attack to give you this final product. This homework for you, you have to try to resolve this homework, and I think is not so difficult for you. So the reaction mechanism for understanding here for understanding only involve deprotonation of the carboxylic acid anhydride, this deprotonation of carboxylic acid anhydride to give anion 4, and then this anion as carbanion, it will be take place already during workup, beta hydroxycarboxylic, this it will be react with this aldehyde to give you this intermediate. Finally, hydrolysis meaning all these molecules, all this part here, it will be alone, and this part it will be removed from the structure. This part it will be removed from the structure as carboxylic acid here. So to give alpha beta unsaturated carboxylic acid. If the starting anhydride bears only one alpha hydrogen, the dehydration step cannot be take place. That meaning if just one hydrogen we have here, two alkyl group, just one hydrogen removed to give you carbanion, and carbanion it will be add to give you this. That meaning we don't have another hydrogen here we don't have another hydrogen here. So that meaning if the anhydride don't have another hydrogen, that meaning the dehydration step, this cannot be happen. This step cannot be happen because there is no beta hydrogen to remove to lose water molecule. Okay, to lose water molecules. Hale-Volhard-Zielinski reactions, also this related with aldol condensation, is a alpha halogenation of carboxylic acid. Alpha halogenation of the carboxylic acid also it has a special mechanism actually this type of reaction. So by application of the Hale-Volhard-Zielinski reaction, the alpha hydrogen of the carboxylic acid one, this it will be replaced by bromine olechlorine to give alpha bromo or alpha chlorocarboxylic acid respectively. Okay, so by using Br3 Br2, this is the we will explain here the mechanism. So firstly, if you look to the phosphorus trifluoride or phosphorus trichloride here, the anshape for the electron on the oxygen for the carboxylic acid, it will be attack the phosphorus atom to give this intermediate product, and then the leaving group, the X minus, it will be add across to the carbonyl here, to the carbonyl to give this intermediate product. Finally, all this it will be play as leaving group. All this it will be play as leaving group. So this make double bond, and this it will be convert to here. This the halogen take the hydrogen as minus HX, and this will be leave the structure to give acyl halide. So secondly, acyl halide it will be react with the HX. Okay, with the HX with the acid it will be react with the X. So protonation it will be take place, and then the halogen here, the halogen will be take the alpha proton طبعا to give carbanion. This carbanion is stable by by resonance. Okay, مهم. Take a proton, give you carbanion, give you a double bond here, and this will be open, and this will be open here to give you the enol form. Enol form. Finally, enol form here, it will be add to the halogen. This make double bond, and this pi bond, it will be add to the halogen to give you this intermediate, and deprotonation, finally deprotonation to give the alpha halo acyl halide. So final step is the reaction between the alpha halo acyl halide, this with the water. The water will be added across to the carbonyl, and this is X, the halogen is leaving group, it will be leave the structure. Finally, the halogen take proton from the water because this oxygen is positively charged. Put positive here, and to give the alpha halo carboxylic acid. This is the mechanism. Okay, this is the mechanism. Try to solve it. So it is important mechanism actually. Also, for example, for here, look to the phenyl acetic acid here. It will be entered to the alpha halogenation. Look Br2, BBr3, H2O minus HBr to give the alpha. This the 2 bromo, يعني alpha bromo 2 phenyl acetic acid. So as a note, the alpha bromo, this the compound, or alpha chlorocarboxylic acid, this are good intermediate. They are important intermediate in organic synthesis. They easily can be converted to the hydroxyl group by reaction with water, or with the convert to the nitric group with the reaction with HCN. This nitric group also is important to be go to the hydrolysis to give the saturated 1,3-dicarboxylic acid. This 1,3-dicarboxylic acid is also, it is important type in organic chemistry. Also can be react with ammonia to form alpha amino acid. This alpha amino acid, you know, the amino acid, they are important also to build the DNA or RNA in the body. So the amino acid is important, and for this reason this type of compound, they are important in organic reaction. So the Cannizzaro reaction also is related with aldol reaction here. Cannizzaro reaction is in the presence of concentrated alkali, يعني in the presence of the base aldehydes containing no alpha hydrogen. Look at this aldehyde with no alpha hydrogen. It will be undergo to the self-oxidation reduction. We said redox. Reduction oxidation. We said self-oxidation reduction to yield mixture of an alcohol and salt of the carboxylic acid to give you two compound, alcohol and carboxylic acid. It is not condensation. You have to be careful here. It is not condensation. Cannizzaro reaction, it is not condensation. Okay, it is not condensation. So here we have different situation, but you have to know it. If you used aldehyde or ketone with no alpha proton, so sorry, not the ketone, just the aldehyde with no alpha proton, so it will be under to the self-oxidation reduction. We said redox to yield alcohol and carboxylic acid. So example here for some aldehyde without alpha hydrogen, this is the aldehyde, formaldehyde, 2,2-dimethyl, 2,2-dimethyl, propanol, benzaldehyde, all this 2-hydroxy, 2-methyl propanol, all this they are aldehyde with no alpha proton, So in Cannizzaro reaction, nucleophilic attack, the hydroxy ions act as nucleophile and attack the carbonyl carbon of the first aldehyde molecules. This form tetrahedral intermediate known as hydrate ion. So the secondly, hydride transfer, the negative charge on the oxygen of the hydride ion, it will be transferred to attack the carbonyl double bond, so it out of the hydride anion. Thirdly, proton exchange. Proton exchange, the carboxylate acid become carboxylic salt. Okay, because the proton, it will be transferred from one to the other, and alkoxide become primary alcohol. So if you look to here, firstly, the base attack the carbonyl, and this will be open to give you this. Now, when this minus, it will be make pi bond, this hydride, it will be leave the structure, leave to attack the second molecule, to attack the carbonyl to the second molecule, and this it will be open to give you this carboxylic acid and alkoxide. Now, carboxylic acid and alkoxide, now we have proton exchange. This minus here take a proton to give alcohol and carboxylate anion. Alcohol and carboxylate anion. Okay, I think it is a clear, easy mechanism, also clear mechanism. So, also we have crossed Cannizzaro reaction. If the aldehyde, they are different, or both of them without alpha proton, so the yield here it will be also give all possible yield of one of aldehyde or formaldehyde, of one of them is formaldehyde, the reaction yields almost exclusively salt of the formic acid. It will be دائما always give you the formaldehyde, it will be converted to the carboxylic acid to give you the salt of the formic acid. This is the formic acid. Okay, and the second molecule, it will be alcohol. It will be alcohol. So look to this and this molecule, benzaldehyde and the formaldehyde. Here, this it will be converted to the carboxylic acid, and this it will be converted to the alcohol. This alcohol and this carboxylic acid. This also important note, you have to be careful about it. This it will be carboxylic acid, okay, and this it will be alcohol. Sorry, this it will be alcohol. So here we have two aldehyde. One of them it will be carboxylic acid. One of them it will be alcohol. And finally this it will be by reaction with the formalin. Yani if you put the formalin here, put the formalin here, the formalin it will be converted to the formic acid here, the formic carboxylate, and this it will be alcohol, and this it will be alcohol. This it will be alcohol. Number 4 here, Wittig reaction, synthesis of the alkene. Wittig reaction, synthesis of alkene. This we inshallah talk about it in the lecture number 3 for this chapter. For this, see you.